Hi, my name is Guillaume Boileau. Thank you for watching my video. I'm a PhD student at the Observatory of Côte d'Azur. My supervisor is Christensen, and I work with Renate Meyer from Auckland. We work on the spectral separation of the stochastic background for LISA. For the overview, firstly we will talk about the context of what is a stochastic gravitational wave in LISA, and some paper of the prediction of the binary black hole and binary neutron star. We'll talk after about the Fisher information matrix. It's a method to estimate the separation from the frequentist method. We also work about the Bayesian method, the MCHC, Markov chain Monte Carlo. We present some results of Adaptive-McMC with 6 parameters and Fisher information matrix. After we will work about the modulation of the wide dwarf binary in our galaxy. After we will present to you the 10 parameters run of Adaptive-McMC with the LISA noise, BBH and BH, wide dwarf and cosmological. Firstly, what is the stochastic background and what is the prediction of the BBH and NSBH? The stochastic background is a superposition of the large number of independent sources. This is unresolved source. We have in the LISA band the wide dwarf binary in your galaxy. We have also a binary black hole in binary neutron star from LIGO-Virgo band. 2 papers have a prediction of the amplitude of this stochastic background. The first is just a prolongation of the estimation of LIGO and Virgo in the LISA band. The second one is just a simulation of star evolution and prediction of the stochastic background. We saw there is no overlap between the 2 backgrounds. And the last component of the stochastic background in LISA is the cosmological sources from the early universe. So we want to have the limits of the measurement of this component. This is our job. And we can estimate, we have modelized the energy, spectral density of this component. On the first step, we can take just a power law with the amplitude omega alpha and the slope alpha. We use as a frequency ref 25 Hz for all the next of your presentation. We have alpha equals 0 for the cosmological component, just for the last one, cosmological sources, early universe, and for the component from binaries, we have 2/3. We have wide dwarf binaries, binary black hole, binary neutron stars. We work about the Fisher information matrix. The Fisher information matrix is a method of the frequentist vision of the data. We use the covariance matrix. In the covariance matrix, in your case, is it just a diagonal matrix? We have the 3 channels, A, E, and T. The A and E are scion channels. This is because there is SA and SE. SA and SE is just a summation of all the components of the stochastic background. So you have the summation. This is proportional of a summation of stochastic background. And T and channel T is just the node channels, and the node channels help the scion channel to converge with the parameters. NE and E and T are just depending from the LISA noise. 2 parameters in our case. Markov chain Monte Carlo. We use the Markov chain Monte Carlo, the Bayesian vision, to estimate, independently to the next vision, the stochastic background. So we use the same covariance matrix, here you have C-1, to estimate the likelihood. The likelihood is just a Whittle likelihood, and you have a version of the summation of the three channels. MCHC is just a method to estimate the posterior distribution. This is an iterative method to estimate what is the parameters. So we just compare two candidates and we conserve the good candidate if the likelihood is better to the other likelihood generated with the other component. And we can build a chain. At the end of the iteration, we have one channel by one parameters. And with the estimation of distribution of the chain, we can have an estimation of the posterior and the estimation of the parameters. In our case, we use 6 parameters, 2 for the component from cosmological, 2 from the component from the galactic, with omega and alpha, and 2 other from the LISA noise from position and noise from acceleration. Result from 6 parameters adaptive MCHC. The adaptive MCHC is just a method to draw the candidate. We just use with a covariant matrix C the estimation with a other candidate to estimate the candidate. Here you have the uncertainty of the estimation of the cosmological amplitude. On the axis you have omega 0. This is omega alpha equal 0. This is the omega of the cosmological amplitude. So you chose to make a variation of the cosmical amplitude between -13 and -8 and see what's happened with the measurement if you have a low cosmological amplitude or a high cosmical amplitude. This is you have also four input of astrophysical amplitude, and we can see the influence of the cosmological amplitude, of the astrophysical amplitude. In the line plot, you have the Fisher study, the Fisher information study, and in the scatter plot, you have the MCHC study. You see an overlap between the vision of the frequentist and the Bayesian. You can see also another thing. This is here the uncertainty. The uncertainty is just the ratio between the error, the delta omega 0, and omega 0. This is the output, the estimation from the two methods. Here you chose to have measurement of the stochastic cosmological amplitude if the error is less to 50%. More of these limits, we consider the measurement or not. We consider no measurement. So, for different amplitude of the astrophysical background in the LISA context, so we use the acceleration noise and the optical metrologic system, and up from the proposal for 4 years of mission data. So you have four estimation of the cosmological limit we can observe with an input of LISA noise and astrophysical amplitude. We see, if remember, we have no overlap of the prediction of the BBH and NSA-BH amplitude. Here you can have an estimation of the limit of the measurement of the cosmological amplitude with an astrophysical amplitude. This is a paper in preparation. So, the modelization of the wide dwarf binary in our galaxy. The first component of the stochastic background is the wide dwarf binaries. So, we can use some simulation, for example, a Lambert last year. In black, you have 35 million of binaries, of wide dwarf binaries. This is all the binaries of the simulation. In red, you have binary with SNR superior to 7. And in green, we use a LISA beam plus the SNR superior at 7. With the LISA, for the LISA beam, we use 4 years of measurement. You have 1/4000 binary result in our estimation. You can generate the cosmological, the gravitational signal for all the binaries, and we can stack all the signal to create a stochastic signals. This is what you see here. We use in the LISA context the gravitational signal. You see here the 5 type of population of the wide dwarf population in LISA. You see here there is carbon oxygen is, for example, the I component of the waveform. In LISA we can't distinguish the 5 type of population, so we have a summation of all the type of population. This is the wide dwarf binaries C by LISA. You see here the modulation from the LISA orientation. Some moment the orientation of the constellation of LISA see the middle of the galaxy. This is when the waveform is maximal. Other moment, LISA don't see the middle of the galaxy, so the waveform is less, has less amplitude. This is why we have a modulation of amplitude. If you add to this signal a cosmological background, this is a flat without modulation. So some moment we can have a better measurement of the cosmological component because we have a less wide dwarf binaries component. Here you see just an estimation of the modulation of the wide dwarf binaries. You see in the blue line just an estimation of the amplitude, the omega A, the spectral density amplitude, from the standard deviation of the waveform in the time domain. You have here the equation to transform the STD to the omega A amplitude. In the red scatter, this is 50 adaptive MCHC of 8 parameters, BBH plus wide dwarf and LISA noise. You see here a good estimation because you have an overlap between the two independent methods. If you consider the total waveform without the modulation, we have a bad measurement of the wide dwarf because this is, for example, the brown scatter, and we see we have no overlap with the red scatter from the Adaptive-MCMC and the blue from the STD. So this is just an example of Adaptive-MCMC at 8 parameters, BPH, white dwarf, and laser noise. For the input, we use laser noise from the proposal. We use A3. This is the component A3 and alpha 3. This is the BBH and BNS background. We use 4.4 minus 12 with a frequency ref is the frequency 2 pi L divided by C. We use alpha 3 is equal to 2/3 for the wide dwarf, because the wide dwarf we saw at the previous plot at the amplitude spectral density. When the amplitude increase, you see less binaries. So this is a broken law on the energy spectral density. At the high frequency, we lose the power law, but at the low frequency, we have the power law, and this is the same slope because this is a binary spectrum. Here you see the estimation. Here you see the corner plot of the estimation. So we have a good estimation of BBH and BNS. 4.46 minus 12 with a good error, and alpha it's near to 2/3. For the wide dwarf at the low frequency, we have an amplitude similar to the estimation with the standard deviation, but we have a large error. It's because we work at the low frequency. We have not a lot of points to estimate this background, but we have a good slope. So now you talk about the 10 parameters run of Adaptive-MCMC. Laser noise, 2 noise, BBH and BNS, 2 parameters, wide dwarf, 4 parameters, and cosmological background, 2 parameters. This is the large context of stochastic background in LISA. Here, this is the study of the Fisher information matrices and Adaptive-MCMC. You see here in different color the line plot, 1 year, 4 years, 6 years, and 10 years of mission. You see in the dash line the limits of 50% of the measurement of the wide dwarf of the cosmological amplitude, and in the scatter line you see the result of Adaptive-MCMC. We chose to make some MCMC estimation between -8 and -14. This is to estimate how it's possible to separate the cosmological component from the other source. You see here a good overlap between the Fisher information study and the MCMC study. You see another thing. You see there is no influence of the time duration. If you come back to this plot, you see at the low frequency the red dwarf. The cosmological, it's in the middle frequency, near to 10 minus, near to the millihertz, at the frequency of millihertz. After you have in the little band the BBH from black hole and neutron star population. And after you have the noise at the very high frequency. It's because the time duration have not a big effect on the measurement. Here you can fix a limit of the stochastic cosmological amplitude measurement. We can measurement on the biggest, on the more important context of stochastic background of near to minus 12, amplitude of minus 12. The principal limitation for the cosmological background is the BBH and SNBH. For the conclusion, we have different techniques to measurement the cosmological component. We saw two visions, the Bayesian and the frequentist method, and we saw similar results. We can fix in the large context of data. We can have a measurement limit between minus 13 and minus 12 for the cosmological amplitude with this method. For us, the principal limitation is not the listen noise. This is the BBH and BNS stochastic background. Thank you for watching.